Okay, so the next set of definitions, we're going to talk through what are strong electrolytes, what are weak electrolytes, and what are non-electrolytes. So there's definitions inside of this. So try and hang on to that framework. What's a strong, what's a weak, what's a non-electrolyte? The first thing we're going to talk about is what is a strong electrolyte. So strong electrolytes include soluble salts, strong acids, strong bases. So remember, if your solution is a strong electrolyte, that means it's going to produce lots of ions in the solution. And because you have lots of ions, you're going to be able to easily carry those electrons through your solution. So there's three things that kind of fall into the category of strong electrolytes. These three things, when you take the salt, when you take your crystal of all of these three things and you put it into your solute, probably water, the crystal is going to completely break apart into ions. So there's three things that do this. There's three things that when you put the crystal into water, they completely break into ions, and those are soluble salts, strong acids, and strong bases. So let's break these three categories down a little bit. All right, soluble salts. So we kind of talked about this already. Remember, a salt is anything that's an ionic compound. So it's made out of a cation and an ion. Now, in order to be soluble, that means it dissociates probably completely into ions. So when you put it into water, it dissociates completely into ions, and there's no solid left. There's no crystal form left. There's no lattice form left floating around in the water or at the bottom of your beaker. It's going to completely dissolve into ions. Here's an example with barium chloride. If you start with solid barium chloride and you put it into water, it's going to dissociate completely into barium. That should be a 2+ and 2 chlorines. So there's virtually no solid form, no lattice form, no crystal form of barium chloride left in the solution, which means barium chloride is a strong electrolyte. You put it in solution, completely breaks into ions. You have lots of ions present to carry that charge. In a similar way, acids and bases can act like this too. So let's take a minute and kind of define acids and bases. I'm going to give you a partial definition of acids and bases. I'm going to give you kind of the easy ones, the really obvious ones right now. And when we circle back to acids and bases later on in the year, when we actually go through the acid and base unit, we'll look at some of the more tricky definitions of acids and bases. So for now, let's just talk about the really basic forms, really simple forms of acids. Okay, so historically, the term acid came from this word sour, because that's how they identified acids at first. Acids are sour, right? You put them on your tongue and you get that like sour, cringy feeling. So if you think of anything sour, lemons, limes, vinegar, Cabbage Patch Kids, all of those have some form of acid in it. And historically, the first acids were obtained by the treatment of minerals. And the first ones kind of identified were sulfuric acid and nitric acid. This is true today too. So anytime you have a treatment of minerals, especially in mining, a lot of times your byproduct is some form of acid, which becomes a problem in the form of acid runoff, right? So if you take environmental science and you start to study mining, you'll learn more about that production of acids through the treatment of minerals. Okay, so strong acids dissociate completely in water. That is the definition of what a strong acid is. You put the acid into water, it dissociates completely into ions. Virtually every molecule dissociates to produce ions. Now, there's a list of strong acids that you should have memorized. That was in your summer homework, but we can go over this again. So before we go over that list, I want to talk about how do you identify an acid. So an acid, notice in a reaction, is always going to result in more H plus present than there was before the acid acted on it. Another way to identify, if you look at the molecule itself, notice that all the molecules start with hydrogen. If a molecule starts with hydrogen, it's probably going to be an acid. So there's two definitions that we're going to deal with right now. The first definition of an acid is an Arrhenius acid. So it's something that gives off H plus when it's dissolved in water. So for example, hydrochloric acid, when you put it in water, it falls apart. And one of the things it falls apart into is hydrogen, right? That makes it an acid. H2SO4, when it falls apart in water, one of the things it's going to fall apart into is hydrogen. That makes it an acid. Now, notice in the case of sulfuric acid, when sulfuric acid falls apart, it only gives off one hydrogen at a time. So we say when something gives off a hydrogen, the term for that is it protonates. So acids are going to protonate one at a time. No matter how many hydrogens are present in the molecule itself, acids are only going to give off one hydrogen at a time, which means your second product here, the other product other than the hydrogen, is sometimes going to have a hydrogen in that as well. Okay, so since strong acids dissociate completely in water, strong acids are going to be strong electrolytes. Okay. Couple important facts about acids. When they are dissolved in water, they are written as aqueous solutions. And so you write them as the molecule with aqueous behind them. Even though in the solution, HCl, for example, exists as H plus floating around and Cl minus floating around, we would still label this solution as HCl aqueous. It's a little deceptive. It would make more sense if we said that H plus was aqueous and Cl minus is aqueous if we labeled it that way. But A, that way's longer. B, this tells you what the source of the hydrogen and the chlorine are, so that you know that, these things didn't come from something else. You could have the hydrogen coming from a totally different source, the chlorine coming from a totally different source, and it would be a very different compound. It would be a very different solution. So by writing it this way, you know where it came from and what some of those properties are going to be. Strong acid is going to completely dissociate into ions. We talked about that. If you have 100 molecules of hydrochloric acid, for example, those 100 molecules are going to fall apart into 100 H plus ions and 100 Cl minus ions. This is what we talked about. Acids are going to protonate one at a time. So if you have an aqueous solution of H2SO4, it's going to contain mostly H plus ions and HSO4 minus ions. In contrast, a weak acid dissociates partially. So we keep saying a strong acid dissociates completely. Well, that's because when it is compared to a weak acid, and a weak acid is going to not dissociate completely. It's going to dissociate partially. For example, if you have, 100 molecules of a weak acid here, what you're going to end up in solution with is 99 of those weak acid molecules still intact, dissolved, but floating around in your solution. And then that one molecule that you're missing has dissociated into hydrogen and acetate, or hydrogen and its anion. So this would be a weak acid. About 1% or maybe even less than that actually dissociates, which is why, check it out, you don't have very many ions in this one, right? So a weak acid would not be considered to be a strong electrolyte. Okay, again, you need to know your list of strong acids. So strong acids include HCl, HBr, HI, HNO3, H2SO4, HClO4, and then some people also include HClO3. So the hydrohalides, the acids that come from the halogens, and then you have nitrate, sulfate, chlorate, perchlorate. Notice hydrofluoric acid is not on there. Hydrofluoric acid is a weak acid. Also notice that phosphoric acid is not on there, and neither is carbonic acid. So if you memorize our table of 8 that we memorized for our oxy anions, right? Carbonate, nitrate, phosphate, sulfate, perchlorate. Okay, almost all of these are strong acids, except not carbonate, not phosphate. And then almost all the halides, the halogens, are strong acid, just not hydrofluoric. Okay, so those are your strong acids. That's a list that you need to memorize. Again, there are some patterns on that periodic table that you can probably pull off to help you memorize those, but we're going to reference those. So hopefully you'll also get very familiar with the strong acid list. Okay, strong bases are the third thing in this strong electrolyte. Again, the definition of strong bases is that they dissociate completely in water. Bases are going to be soluble compounds. Well, bases don't necessarily have to be soluble, but come on. Move forward. There we go. Okay, but they contain the hydroxide ion. That's what makes them a base. So just like acids are going to end up with more H plus in solution, well, bases are going to end up with more OH minus in solution. And actually, it's more of a ratio. If you have a solution that has more H plus than OH minus, you are going to have an acidic solution. If you have a solution that has more OH minus than H plus, you're going to have a basic solution. So it's not that one is present and one is absent. It's that the ratio is slanted a specific way. And then hopefully you are now asking, what happens if H plus is equal to OH minus? Can you think of the answer? Yeah, that solution would be neutral. So think of it more in terms of a ratio. But obviously, if you put something in your water and it produces one, that ratio is going to go towards that side. Similarly to acids being sour, bases are bitter. So most things, if you find something that is bitter and slippery, it's probably a base, which is most of your soaps. Soaps are bitter and slippery, and most of them are bases. Common bases you're going to come across are sodium hydroxide, potassium hydroxide. So notice that again, it dissociates into Na plus and OH minus. And actually, anything that comes from the 1A or the 2A family, any hydroxide that comes from these families is going to be considered a strong base. So any alkali hydroxide or alkaline earth metal hydroxide is going to be a strong base. There are some exceptions there, but we can talk about those later. Okay, before we get on to weak electrolytes, I just want to say one more thing about bases. So you know how we talked about acids protonating one at a time? Well, bases don't do this. So if you have a base, let's say we have magnesium hydroxide. If you have a base that contains more than one hydroxide, it's going to dissociate into both hydroxides at the same time. So magnesium hydroxide is a strong base. When it dissolves, it is going to give off both hydroxides at the same time. So this is a difference between bases and acids. Okay. Oh, that's not what I wanted. So those are your strong electrolytes: soluble salts, strong acids, strong bases. Your weak electrolytes also are going to have 3 different categories. So weak electrolytes are going to, when you have your crystal or your lattice, okay, and you put it into water, what's going to happen is part of that crystal or lattice is going to dissolve into ions. But the rest, the vast majority of that lattice or crystal is just going to dissociate into molecules. So you'll have a bunch of molecules floating around. So the lattice will dissolve into molecules. But not very many of those molecules will actually split up into ions. And again, we talked about how it's about 1% or maybe even less than 1%. So for every 100 molecules of acetic acid that you put into your beaker, 99 remain intact as molecules. Only 1 out of that 100 is actually going to produce your hydrogen and then your anion. This means acetic acid is a weak acid. Now, when you're looking at those lists of strong acids, anything that's not on that list is going to be a weak acid. So that's why we memorize the strong acids, but because there's only really 6 or 7 of them. And that means that everything else we encounter is going to be, we can just automatically assume it's a weak acid. Now, our most famous weak acid by far is acetic acid. It's cheap, it's abundant, and it's fairly harmless. Acetic acid's the acid that's in vinegar. So instead of buying acetic acid, we can actually just go buy vinegar and use that. And so acetic acid is by far going to be your most common one that we deal with in class. Similarly to weak acids, weak bases do the same thing. So if you have a weak base that gets dumped into water, the majority of that weak base are going to remain intact as molecules, and only one of them is going to really fall apart into the hydroxide. Well, okay, so here's the catch on weak bases. Most weak bases don't produce hydroxide. Most weak bases actually interact with water and break water apart, and in breaking water apart, it produces a hydroxide. So our most famous weak base is going to be ammonia. Here we go, right here, ammonia. Okay, and here's what happens with ammonia. Ammonia, if I draw the Lewis dot diagram, looks something like this. And notice that nitrogen, which is an extremely electronegative element, has extra electrons on it. So that nitrogen is very, very negative. It's still partially negative. It's still not a complete negative, but it's extremely negative, which means it's going to have a very high attraction to things that are positive or partially positive, like hydrogen. And so what happens is every 100 molecules, out of every 100 molecules of ammonia, about one of those ammonia molecules is successful at stealing the hydrogen off of water. And what that forms is ammonium, which is this molecule, NH4+. And look what's left over once that hydrogen is stolen off of water. You're left with a hydroxide. And so ammonia as a base, it doesn't give off hydroxide on its own, but it does produce hydroxide in solution. Now remember, this doesn't happen. Not every ammonia molecule is successful at stealing that hydrogen off of water. In fact, if you pair up 100 ammonias and waters, only one of them is going to be able to do this. So water is better at keeping that hydrogen than ammonia is at taking that hydrogen. But it does happen 1 out of every 100 molecules, and that's enough to produce a fairly basic solution. It is weakly basic, but it is still decidedly basic. So again, weak bases will produce some ions in solution, which make them weak electrolytes. Okay. A couple notes here. Notice that ammonia is written to indicate 2 different hydrogens. So this first hydrogen is an acidic hydrogen. These other 3 hydrogens are not acidic. They will never dissociate ever. And if we look at the actual molecule itself, okay, notice that ammonia is what? Look at this ending. What's ammonia? Think organic here. It's a carboxylic acid, right? It's ethanoic acid. And so these 3 hydrogens here that are attached to the carbon are not going to be able to be taken off of carbon. But this hydrogen here, these electrons are going to be pulled very strongly towards oxygen, because oxygen is so electronegative that it leaves this hydrogen here almost like bare or free of electrons. It's very partially positive, and so it is going to be more easily dissociated. Whereas carbon and hydrogen tend to have very similar electronegativities, and so these electrons here are shared fairly equally between the 2 atoms. And so this hydrogen is not going to be able to be stolen away because it's not very charged. It's very securely bonded to that carbon. And this is true for lots of acids. If they have multiple hydrogens, the acidic hydrogens are going to be listed first in the formula. Non-acidic hydrogens are going to be listed later. And that's why we as inorganic chemists write acetic acid like that. If you're an inorganic chemist, you'll write it like this: CH3 COOH. So inorganic chemists care about structure, and when you write it like that, you are indicating the structure of the functional group. Whereas we as inorganic chemists don't really care about the structure. What we care about is the behavior. And so we care that it behaves like an acid, and so we write it like this top form with the acidic hydrogen very clearly written off to the side. Okay, last category, non-electrolytes. So these may dissolve in water, but what they're going to produce are molecules, uncharged molecules, neutral molecules. They may have partial charges in them, but they're not going to separate into distinct ions that will move apart from each other. So there will be no charges to support the movement of these electrons. Most of these are polar molecules. Ethanol is a good example, ethanol is the alcohol that's in your mouthwash. It dissolves very nicely into your mouthwash. When it dissolves into water, it's going to dissolve the entire molecule, and that molecule is not going to break up into ions. And actually, usually when you have organic things like this, organic things tend to stay as molecules and not break apart, mainly because of what we were just talking about, how the carbon and the hydrogens are very similar in electronegativities. Those electrons are shared fairly equally, which makes that bond extremely stable. And nothing, especially not water, is going to be able to come along and steal off part of it to make an ion. So most organic molecules are very stable. If anything, they're polar, and they're going to dissolve as molecules and not break up into ions, and therefore not be able to carry a current. The oses are the same: sucrose, glucose, fructose, all of those, the sugars, similar. Notice they're organic molecules too, right? Carbons and hydrogens make up the majority of these, and sugar dissolves very well into water, but it dissolves into molecules and it doesn't break up into ions, and therefore it's not going to be able to carry a current. So these are probably our most common examples that we're going to run into of non-electrolytes. Okay, so that gets us through the bulk of the definitions for solutions. So I'll see you in class, and we'll do some of the practice now with all of this stuff.